Hi, today I will be talking about the dehydration of methanol to form dimethyl ether. The problem we are approaching is designing a packed bed reactor to do this reaction. The dimethyl ether will be converted from methanol and the side product will be water. The feed to the reactor is going to be 700 kmols per hour of a not completely methanol feed. The other portion of it is water. The assumptions we made is that the PBR is proven to provide the best conversion of DME. The reactor is going to be isothermal, but not isobaric, meaning the volumetric flow rate will not be constant and that there is a pressure drop within the reactor. The reaction is also going to be assumed to be irreversible. A DME production rate of 100,000 tons per year will be one of our design goals. The conversion will be 80%, and the product is going to hopefully be 99.5 weight percent DME. The goals were specified in the problem statement. This is our stoichiometric reaction. So 2 moles of methanol are fed, and 1 mole of DME is produced, as well as 1 mole of H2O. From now on, we will refer to methanol as A, and DME as B, and water as C. Ethanol will act as an inert component to this reaction. Al2O3 is commonly used for the methanol to DME process. One, because it has a large surface area and it increases the reaction rate. And the thermal stability of the catalyst itself means that it will be unaffected with changes in temperature, which are always possible in a reaction like this. Now I will go into the material balance. The material balance is very important to every different part of engineering, as it makes sure that we take into account that all of the material still remains there and none of it is getting destroyed. Our material balance that we will be going off of is input minus output plus generation minus accumulation equals 0. The equation below shows the flow rate of A into the reactor, FAO, minus the flow rate of A out of the reactor in moles over the initial flow rate of A. This equation will give you the conversion, and to set our goal of 0.8 or 80% conversion, we set this equation equal to that amount. In order to determine how much A is going into the reactor, we had to multiply the mole percent of A of the feed going into the reactor times the amount of moles going into the reactor, giving us 679 kmols per hour going into the reactor of methanol itself. The remainder of that is made up of water. Next, we solved for the moles of methanol out using the above equation, setting it at 80%, and we came back with 135.8 kmols per hour of methanol out of the reactor at this selected conversion rate. The stoichiometry equation relates each component to our base component, which in this case we chose methanol as our component that we're referencing everything to, and that is why the conversion was determined using A as well. Using the stoichiometric coefficients from the initial equation, you can determine the amount of each of the components that will come out of the reactor at the conversion rate X, which in our case is 80%. So as you can see, the stoichiometric coefficient for A is 2, which is why you end up with 1/2 times 0.8 times the entire amount of A going into the reactor in order to get the amount of DME out of the reactor, which is FB, giving us 271.6 kmols per hour out of the reactor. Same can be done for the amount of water out of the reactor. And in this equation, you end up seeing that we will have about 278.6 out of the reactor, as you have to also add the amount that went into the reactor to this amount that's being produced from the reaction itself. And that's what the first term in that equation is accounting for. Next, going into the energy balance. Energy balances are important because we need to know how much energy is being created or lost in our reactions. And though the energy will then translate into things such as temperature changes, we need to know that for safety purposes. So, as you can see here, we evaluated the enthalpies of the reactions. We had to do this for each component by applying the second equation down on the page to each individual component in the reaction and solving for that. And then we combined all of that in the above equation to solve for the total change in enthalpy, thus giving us our Q value or heat transfer value in and out of the reactor itself. N stands for the number of moles, so it is mole dependent, and therefore the flow rate into the reactor, if we were to change that, would end up changing the enthalpy of the reaction. The reaction rate is another big portion of any chemical reaction engineering problem, as the reaction rate affects the speed of the reaction and how long it has to be in contact with the catalyst in this case. So here is a differential equation representing the relationship between the weight of the catalyst, which is directly correlated to the area of the catalyst, and the reaction rate, as well as the conversion. So assuming the pressure drop is negligible, we can use that to solve this differential equation. And if you assume that, then you can integrate to find the below relationship between the conversion and the weight of the catalyst. Though we did not assume this as something that was solid for our particular calculation, this is one way to simplify the calculation itself. When we do want to account for pressure drop, we do have to use the Ergun equation. And in a packed bed reactor, pressure drop is heavily affected by the catalyst weight. The following equation gives a parameter to account for the pressure drop, and it is a ratio of the pressure coming out of the reactor, P, over the pressure going into the reactor. And that tells you just about how much the pressure is changing throughout the reaction. As you can see, the Ergun equation is applied in these cases with a pressure drop, and it relates things such as the superficial velocity and the spacing between all of the catalysts to the pressure drop in the equation. So the alpha is a parameter that we use in that equation, and the equation is shown below for alpha. And as you can see, it's dependent on the cross-sectional area, as well as the density and the void fraction. So the effects of varying the reaction parameters can be shown using this ratio of Y over the catalyst weight. So in MATLAB, we went ahead and varied these different parameters, the parameter shown before and catalyst weight. And as you can see, the higher the ratio, aka the less pressure drop that you will see, correlates to the smaller catalyst weight. As you can imagine, there's a lot less drag when there's a lot less catalyst. So if there's zero catalyst in the actual pipe, you can assume that the pressure drop will be pretty close to negligible, depending on the walls and things like that. There still will be a small amount, but it'll be negligible in comparison to the amount that adding catalyst will end up putting into that packed bed reactor. And for conversion, the effect between conversion and catalyst weight, you can see here, relates also to the reaction rate and the initial flow rate. And as you add more and more catalyst, the conversion is going to become higher. This would make sense because the fluid is actually going to be slowing down, so it will have more time in contact with the catalyst, but it will also have more surface area, and thus having more surface area of catalyst means more atoms and more molecules will become contacted by that catalytic surface. Now to go over some safety parameters for this particular experiment. DME is highly flammable, so that's why we do things such as enthalpy calculations, and because it can have a dangerous fire hazard component to it. The adequate training of personnel is also very important. Wearing The correct PPE is very needed as well as regular medical checkups when you're doing this on a large scale to make sure that there are no chronic effects of the materials being used. Preventative and total productive maintenance strategies should also be applied to the equipment. Emergency training should be done regularly. Steam traps and security valves should also be equipped, especially when handling the high pressure environment that this is or could potentially be. DME containers should also be handled with care, and a cylinder valve should be checked to be closed and not leaking, as DME can be harmful to people in the environment. Thank you. This is the end of our presentation.